Okay, so stress X of gamma, okay, of gamma is equal to minus mz over izz, right? So we know that at gamma, y is what? Positive, right? So this is equal to minus mz over izz multiplied by y. Okay, so we have over here at alpha, this is now in tensile, gamma now is in compression. Okay, so we are aware that this is under compression and the top end is under tensile. Okay, so now now we are going to draw again the bending moment vector. Okay, so the bending moment vector will go in this direction. Okay, so the moment is in z, right? Some of you might ask me, Eugene, why is the moment in z? Okay, and I do apologize, I have to have drawn this. So over here, this is rotation in the what? Z direction, right? This is the rotation in the Z direction. So if you look at the rotation in the Z direction, right? If you look at the rotation in the Z direction, this curvature over here, right? And this curvature over here, they have the same what? They have the same direction of curve, yes or no? Right? So if that's the case, it is in the Z direction. Okay. So a simple thing to remember is that when moment is in Z direction, the second moment of area is also in the what? Z direction. Now, it is different from shearing stress, right? If we look at shearing stress, right? If we have if we have if I were to go up, can you all see my screen? Yes or no? Yeah, I think you can. So if you were, is anyone else not seeing the notes? Are you all seeing the notes? Yes. Okay. So if we want to go up, right? If you look at the shearing stress, right? The shear force in the y direction, the second moment of area you take in the z direction. For bending moment, if your moment is the z direction, you take the what? Izz. Okay. As I say, this is going to be important later on when we do two directions. Okay. When we're dealing with two directions, that is going to be important. Okay. Now, anyone, any questions so far, please? Anyone? No? I have no questions? Okay. So now the question now, can you
Sorry,
repeat?
I have a question.
Yes.
Yeah, so where this minus comes from, like the minus that we have originally in the formula,
It,
minus m.
yeah, it is the root formula, okay? Is the formula that we have to apply. I'm not going to derive it, but basically this formula over here, yeah, I'm going to show you now. This formula over here is what we have to apply, right? This formula that that my cursor is pointing out. Can you see my cursor? Right?
Yeah,
That is the formula that we have to apply. Now I'm just explaining to you, in order to apply this successfully, what you must observe. Okay.
okay.
Okay. So
Okay, thank you.
I know it's pretty not abstract, but there are rules that we apply. Like when it's 0, 0, we have 1, 2, 3, 4, 5 increment. 0, then we have minus 1, 2, minus 2, minus 3, minus 4, minus 5. It's a set of rules, okay, that we have to comply, that we have to obey to get the analysis to work. Okay. I'm not going to spend time deriving it. Okay. We can spend like 45 minutes deriving it. At the end of the day, it's not going to give you any more value than what I've just told you. Okay. Right. So now, what what is stress X? Okay. Now, what is this stress X that we are calculating? Okay. What is this stress X we are calculating? Okay. So I'm going to copy the image that we have drawn earlier. Okay. I'm going to copy this image. That image has been, yeah. Hold on. The image has been distorted slightly, and I'm going to correct it. Hold on. You guys just take a less than like 1 minute break, okay? because I said something happened in Microsoft Teams, not Teams. Okay, now I'm going to copy the image over now. Okay, so this is what we had. Okay, so you guys cannot see yet, not to worry, I'll move it down. Okay, so this is what we drew earlier. Okay, this is what we drew earlier, right? So what are we calculating now? Okay, so before I go on further, what are we calculating? Okay, what are we calculating? So I'm going to now take an element. Okay, I'm going to take an element. So I'm going to take an element some over here. Okay, so I'm going to blow up this element. Yeah, I'm going to draw this element bigger. Okay, and then I'm going to draw a transformation. So the transformation is still the same. X, Y, rotation about Z. And you guys have seen this element before. When we were dealing with shearing stress, you have observed this element before. Okay, so now we will have Scott. You say, can you repeat that? What is that you want to repeat, Scott? You want me to repeat, Scott? Oh, it's okay. Okay. So now what we see over here now, right? We are calculating stress in the X direction. Okay, that's the direction we're going to calculate, right? So when we were doing shear, we also did this, right? We did our shear, right? Can you remember? So this is shear, right? The intersecting plane is X. The direction of the shear force is Y. So likewise, this is shear Y, X. Okay. So we have done the shear. Now we are dealing with what? With the normal stress. Okay. And you guys know normal stress can be due to axial loading, which you guys have done in the first 2 weeks, right? Now the normal stress is due to bending. So the normal stress is due to bending. What does it physically means? Okay. So now if we were to draw the cross-sectional view, so I'm going to draw the cross-sectional view now. So when I construct the cross-sectional view, okay, so cross-sectional view at point B. Okay, so we slice this structure. Okay, we're going to cut this structure up. Okay, and this, when we cut, I'm going to show a cross-sectional view now. Okay, cross-sectional view. So relative to our transformation, so I'm going to draw a transformation. Now this is our transformation now. So when I slice it up, we're going to view from the so-called the end view. Okay, we're going to end view. So watch my transformation. Okay, so this is Y, right? This is Z, right? And then we have rotation in the X direction. Okay, so if our cross section of our structure looks like this now, so our structure happen to have a rectangular cross section. Okay, rectangular cross section. Okay, so this is our cross sectional area. We cut it up, and at a point over here, okay, at a point over here, right, this is known as my neutral axis. And let's say the deformation is a smiling face where we apply the load P. So let's say this is our deformation. Okay, so if I draw the deformation pattern, this is our deformation pattern now. Okay, this is our deformation pattern. Right, that's our deformation. So we know that based on that sort of deformation pattern, the bending has to go this way. So M in the Z direction, right? M in the Z direction. So we know at the top, right? At the top, we are going to get compression. At the bottom, we're going to get we're going to see a what? A tensile. Right, we are aware. So now, if we want to sketch the distribution, remember, like what I told you, we're dealing with distribution now. Okay, so if we're going to sketch the distribution, how does it look like? Okay, so we are going to, so we have an axis over here. Right, so this axis is our stress in the x direction. Okay, and over here, right, this is our y. Right, and then to sketch this out, we know that at point at the top, okay, it's going to be compression. Sure. So let me explain further. So in this side of the graph, right, stress x is going to be positive. On this side, right, stress x will be in negative. Right, stress x is equal to negative. Okay, so as you can see now, right, what we have over here, so we know, right, what we have over here, we know that at a certain point y, right, so we know that at a certain point y positive, right, so this what we have is minus stress x and positive y. Right, over here we have negative stress x and we have also a negative y. Right, the y is negative. Right, so in that context, what we have over here is the distribution profile. So this is what we call our distribution profile.
I have a question, sir.
Yes.
At the bottom where you have tensile, you said
Can you please?
that's negative x and
Oh,
positive
it's positive.
y?
Sorry, I got it wrong. Thank you.
Oh, thank
you get a pint of beer. Okay. Yes. Someone have a question? Are we okay?
Sir, can you repeat this?
Yeah, can you please?
Hello? Okay, I will repeat this, okay? So what we are sketching down here, right, is known as the stress distribution profile. Here's a stress distribution profile. Okay, so on if on the right hand side, so this is our right hand side. On the right hand side, the normal stress is in tensile. Okay, on the left hand side, so this is our left hand side, right? The normal stress is in what? Compression. So in terms of y, right? So if this is our y, if it's this direction going up, right? So y is what? Positive, and it's coming down, y is what? Negative. Okay. So we know that at the top, right? At the top where we have y positive is in what? Compression. Okay. So this over here, that's where we have compression. And then when it's y negative, it's in what? It's in tension. Okay, so this is known as the normal stress distribution profile. Okay, now there are arrows that we have to draw. Okay, and this arrow is not difficult to sketch. You just need to understand something. Okay, let's do the compression first. Okay, so compression, the arrow will be pushing towards the y-axis. Right, so that is so in compression, arrow will push towards the y-axis. So we are treating the y-axis like the material, okay? Then in tension, it is pulling away. Okay, right? You can see that, right? In tension, it is, oh, this graph is pulling away. Okay, so that's how you distinguish in a stress profile pattern whether it's compression or tension.